2 minutes to go, guys.
You want to start introducing yourselves?
Okay, I'm Dmitry. I'm from Russia. I wish you good luck.
I'm Riyad Urbana. I'm a professor in computer science and from Tunisia.
Hi, أنا اليوم بكير كوريا من Federal University
My name is Fernando. Translation to Israel.
Hi, my name is Ignacio. I'm from Argentina. I was a former competitor in 2007, so I know how you feel now, so best of luck.
I'm Edgar from Australia, and I was also a former competitor from 2008. And I worked for a startup for 1.1.
I will hold to time to give us another 20 or 30 seconds and the clock to go.
So don't be rather sad today, just smile. You are already winners, so just tell us about your success and that's all.
Guys, that's it. Shall we run it?
Hello, my name is Otilia, and these are my colleagues Victor, Luci, and Remus. We are Team IQube from Romania. We are delighted to present you our solution called LiveX Learning Platform. LiveX Learning Platform provides an interactive and cost-efficient approach to science experiments. In other words, we want to help schools from all over the world to provide science experiments at an affordable cost. Our solution consists of a software platform that runs in the cloud and the end devices, which are off-the-shelf hardware such as phones, tablets, and our innovative invention, the IQubes. Let me tell you very quickly what we'll talk about in the next 30 minutes. First, we will identify the problem our solution aims to solve. Then, we will tell you about the design and innovation of our solution. Afterwards, we will get into the technical details of our architecture. And then, we will tell you how we will sustain our solution for a business plan. Afterwards, we will show you some feedback from our users, and then the benefits of our solution. Going to the first point. As Confucius says, I hear, I forget. I read, I remember. I do, I understand. We, as students, know best what this means. When we learn something new, it's always easier to understand it better and remember it better if we do science experiments, if we put the theory into practice and have that hands-on experience. Let's take this situation. Let us all imagine that we are students in school again, and we learn some very complicated lesson in science. Lots of formulas, very complicated theory. Then, naturally, we imagine what it all means in reality. That's how the human mind works. We try to correlate it with the reality. But most often, imagination is not enough. We need to do something practical to understand it all. So the best approach would be to go in our science laboratory and perform experiments. So let's go to the laboratory. These pictures are taken from a school in the rural area in Romania. The first is their physics laboratory and the second is their chemistry laboratory. They haven't received new equipment for more than 20 years. So they have very old devices which vary in function, and the substances are also very old. The chemistry teacher even told us it's not safe to use them anymore. So we can't perform any experiments here. Taking another situation, this is a school in Nepal, near Kathmandu, where the students had no equipment whatsoever. But in time, they received some computers to make computer experiments. That's not very interactive. The computer simulation is not very interactive, but it's a solution. But here another problem comes up. We need money to buy the software for the computers, and also we need staff to maintain the computers. They can't afford any of this, so therefore their experiments still take place on paper with pencil. And the situation is not local, it's a global situation. It happens in Latin America, Asia, Africa, where often there are no educational materials, so their method of instruction is repetition. It also happens in developed countries, such as the USA, where 75% of the schools report getting new materials. And the importance of this practical education is also emphasized by Thomas Khalil, the Deputy Director for the White House Office of Science and Technology, who says and advises to give every child the ability to become a maker. So all in all, this is a global situation. There is a huge number of schools all around the world where they have no laboratory equipment. And that is because of these prices. For equipment in one laboratory per year, it would cost $3,000 US if we do it with normal laboratory equipment. If we choose computer simulation, it would be around $2,500. And our solution, what we try to come up with, is around $1,000. So we want to do more with less, make it more interactive at a lower cost. So basically, our goals are to provide an affordable alternative to expensive laboratory equipment. Also, give the children worldwide the chance to have that hands-on learning experience. And we want to offer an alternative to unengaging materials. And we also have a goal for teachers. We want to create a community around the solution and help them share their teaching experience. Our target audience are children between 4 and 16 years old worldwide who attend school. That's 1.1 billion children. We aim to reach, in 5 years, at least 1.1 million children. So, what our solution offers is for children in secondary education, we help them to create experiments in subjects such as physics, biology, and chemistry in a more engaging way. But we also have something for kindergarten and primary education. We want to give them a new approach to learning by play, which is more interactive and more fun. I let my colleague tell you more about the design and innovation of our solution.
Okay, so to understand better our solution, the easiest way to see how it works. So the first thing we did when we built our custom cubes with LCDs on each side, we went to our target audience. We went into the kindergartens and gave it in the hands of the children to see how they react, if they like it. And we got really nice feedback from them. So they really loved it and they were really attracted to it. Second, we went also to schools. This is a school from 2nd grade. And taught them the multiplication table with our IQubes. And the children were really amazed. They came up with new ideas, what problems they could solve with these IQubes. So they typically had to match the product with the results there. So basically, our whole project is tailored around the Microsoft vision of 3 screens and the cloud. So we have a software platform running in Windows Azure, which communicates with end devices like off-the-shelf hardware and our custom IQubes. To see more precise how these IQubes work, let's see an experiment. This is a chemistry experiment. We have on one IQube hydrogen, on the other IQube oxygen. If we turn the cubes, we can change the concentration of them. If we match the cubes, they can sense each other. Here we can get a fire. If we increase the concentration of oxygen, we also can get an explosion. There is also sound. Looking at the IQube, we have different components. So we have some wireless communication module, a speaker, LCDs, proximity sensors for the cubes to sense each other, and also RGB LEDs for feedback. Looking at the second example for kindergarten for the 1st grade, here they had to match the word with the number. So if they put it wrong, like 2 with 4, the cubes turn red. Yeah, it's not correct. But if they got the right solution, then they can get positive feedback, so the cubes turn green. I also talked about mobile devices. Let's see an experiment on a mobile device for the secondary education. So here they have a short theoretical description to remind the theoretical aspects, then a methodology, how to produce, how the experiment works, what they need to do, and now they perform an experiment with the inclined plane. So the telephone, we put it in our inclined plane, and after that we can see exactly the trajectory the phone went, and the children can see in every point the velocity and the acceleration in each point. So they can prove it by theoretical performance. So basically, our software platform running in the cloud is open and expandable. It supports any device that has sensors and a display. We only need to write a thin client to them. Looking at our software platform, let's see why we use the cloud. First, talking to teachers in different schools and studying the school program, we saw an on and off pattern because of holidays. So with Windows Azure, it's really simple to scale in these periods. Also, we observed some predictable peaks. So the teacher told us that after the first 3 weeks, they want to put the theoretical aspects into practice and to make experiments. So also, we have periods when we need to scale. Talking about scaling, we want first to start up small with few schools from our region, and then have the ability to ramp up fast to the whole countries and also other countries. We did with Windows Azure, it's really simple to do that. And Windows Azure, we can focus on apps, not on infrastructure. We can focus to bring our solution in front of millions of students. Specifically, with Windows Azure, we used a couple of things. First, service bus is very important for situations to connect the PCS service running in the cloud with endpoint devices where firewalls and make our problems. Also, Windows Azure Content Delivery Network. It's helpful to store, to cache the blob storage in specific areas to increase the bandwidth for the download of different media images to that points. Also, the access control service helps us to easily authenticate and authorize the endpoint devices using Windows Live. So let's see some technical aspects of our architecture.
Right. So before we get on with the architecture, let's look at the data flow. The endpoint devices are just interfaces to the cloud. They collect the data from the sensors, they send it to the cloud, it's processed there, and based on that, the result is given back to the end devices, which in turn take action based on that. So this is a more detailed view of our architectures. Let's look at the endpoint devices. We currently support Windows Phone 7 with its 256 megabyte iteration for developing countries called Tango, and we have an app in the marketplace under certification for that. And we also support our cubes, but at the end of the day, you just need to write a client and you can add any device. This is because in Azure we have Windows Communication Foundation service, which is a common interface that can be accessed from all devices that are capable to connect to the internet. These gather data from our sensors, they control our experiments, and they interface with our user interface websites for web applications. We talked about workflows. We decided to make our experiments as workflows because using workflows through Windows Workflow Foundation, you can create functionality without actually having to write code. You just drag some blocks, which we made. We made some custom activities as well. And this is executable then. You just upload it to the cloud, and the interpreter there does the work. So this is done through our ASP.MVC3 web apps. Here, teachers can create the experiments, since we decided to also let teachers become makers, not just children. They can schedule them, they can deploy them on the devices, and then they can get results back. And also, they can decide whether or not to sell them to other teachers around the world for profit. And this is how the user interface looks. And this is how to create an experiment for the cubes. It's really easy. You just have to drag the pictures from your computer into the designated spaces, configure what you want the cube to do, if you want it to vibrate or you want it to display, to flash the LEDs or display different pictures. And for the business logic, for the logic part, you have blocks in natural English. So if a cube is connected to another cube, then do that. And after this is done, the experiment with all the pictures is automatically downloaded to the cube when the teacher wants it. It's really easy. And this is what we previously did. So this is a multiplication game where you have to match the product on one cube to the result on the other cube. If they match, the color turns green, otherwise it turns red. And like I said, afterwards, the teachers can decide whether they want to share their experiments and their experience with the rest of the world through our marketplace. They can sell their experiments there, they can make a profit, and this in turn should help them become more competitive, wanting to focus more on getting better, to develop quality experiments so they get more customers. And we decided to do our software as a business from the start. And towards that end, we implemented a methodology like Scrum, not that Scrum, this Scrum. We also used source control, we had daily sprints, we used unit testing, and all this because we want to make it a business. And moving on to the business part, Victor will tell you about it.
So let's see how we get our product into the market. So this is basically our engineering model. This is a LiveX kit. It contains 6 iCubes and the following components. So the first part, in orange, is the access to the software platform running in Azure. So basically, we are managing the subscriptions with Azure, and all the costs will be divided to all the schools. So the schools need to pay us just a fee. So in yellow, we have the part of the LiveX kit, which contains the box, the coordinator to connect the cubes with the internet, an inductive charging pad, and 6 iCubes. And also, we can offer some optional stuff for specific needs, like a solar charging kit, a 3G dongle, and also a tablet piece. So here you can see the price, and here the components. And you can also see how the price will decrease in different years, in a 5-year time span. So making some totals, here are the packages. The first one is the access to our software platform. The second one, we also added the LiveX kit with the iCubes. And the third one contains also all the optional equipment. So these are the production costs. With this, to bring it to the end users, we also need to add this kind of costs. So the selling price, the final price, will be like this. Like LiveX cubes, in the 5th year will be around $170. But currently, we are working on a partnership with TechSoup. We spoke with Chris Warman, and he told us that he will help us to bring our custom hardware to different countries because he has connections. He also, TechSoup sells equipment, reconditioned equipment to different schools, and then we can rid up from the distribution and shipping costs. Looking at the sales evolution, we basically want to reach in the 5th year like around 10,000 kits, 10,000 LiveX kits. And all this is based on the number of schools in our country and in the neighboring countries. Also, looking at the projected profit, we need at the first an initial investment of $125,700. So this is not a high investment because a lot of startups start around $100,000. And the first $75,000 we want to reach through the Imagine Hub grant. So having a closer look, this is divided into 2 cost centers. First, we need $45,700 to build, to manufacture our first 300 cubes, and $81,000 for the business. Looking at this cost, we build a model. So we first start with 300 cubes on the left in the first month, and we add a healthy 30% profit of it. and if we invest this profit to build new cubes, then we will reach 3,800 kids. So the total profit from the first year is this, and the second year we will go from the order to back order. So the students will order the cube, they will pay first, and then we will deliver their cubes, so we don't need to invest into ours to make stocks of the kids. Looking at the business, the 81,000 will be spent for this designer business consultancy, Windows Asian market. To break down the profit, 87% comes from the marketplace and 30% from the selling of the live kits. Having a closer look at the marketplace, it is broken down in 84% from the purchase commissions and 16% from some registration fees, individual creators, industrial creators, and also translators who want to translate our experiments in the marketplace. So at the end, in the 5 years, we want to reach 1.5 million students and also to gain the money to sustain and develop our project even further. Looking at feedback, we talked to a lot of teachers and they were really delighted about our solution. The kindergarten teachers wanted to ask us when we can implement it, and they were delighted to bring our solution into the classrooms. We also have investors, some sponsors that sustained our project, and let's revise sort of the benefits of our solution.
Yeah, to sum up the benefits of our solution, it is cost efficient, it offers hands-on experience, it's a long-term solution, it will easily be adapted to new devices, and it's very, very engaging, as you saw in the feedback. And for that, let's make the children of today the makers of tomorrow. Thank you.
Let me begin. You have very interesting technical story, but let's begin from the very beginning. When specialists today are talking about learning process, they often use the idiom called Lego catastrophe. It's about why you are sure that your learning patterns are useful for children, because how they will get system approach in physics, etc., while just playing cubes like babies. Did you ever talk to specialists in cognitive theory or something?
Actually, the cubes are more focused on the primary education. For physics and for secondary education, we talk more about the phone solution and other devices we will implement. For example, we could use the Windows Phone sensors such as the accelerometer, magnetometer to measure speed, acceleration, magnetism.
So cubes are all about primary education?
No, you can also use them for secondary education, such as the chemistry experiment. But they are really for primary education. And there's just
think about this process itself. When you all has an opportunity to have right answer, just playing with and not thinking. So that there is big questions with cognitive theory in your approach. Technically, it's all right.
What is the most complex part of your project?
Our IQubes are the most complex part of our project. The cubes are an electronic device that can communicate with each other and with the cloud. We have some pretty amazing electronics inside them, lots of sensors, and
What is the price you expect for each cube?
For one cube, yes. We talked with a local investor. He was ready to invest in us when we have a solid project, a solid working project. And he told us, okay, give me the project, I make you the tools from the $10. The piece, $10.
Including every sensor and everything?
Yeah, just one cube.
I expect so it's quite complex device.
Guys, you mentioned that you've got about 85% of your market share predicted coming from the marketplace. Is that correct? Actually, if you can tell me a little bit more how you thought the marketplace would work in terms of ensuring quality apps come through and how you verify them, and how people buy them, how that whole process would work for you.
Well, the marketplace should allow the teachers or any kind of user to select first the education level. So if he chooses the education level he wants to select the experiments, and after you choose the education level, there will be a list of subjects, and then for each subject we have a list of experiments, and the experiments have the description of the language, the necessary system requirements, if they work for the cubes or for the phone. They also tell you about what's needed to implement them, the theoretical knowledge, so we will have a short description. We are also thinking to translate them, to hire in the future translators to translate them in other languages, and perhaps even staff to verify the correctness of them. So that's a future business.
Yeah, and also for registration, there is also a fee to responsibilize who wants to put experiments there, and when after uploading, we'll also test and verify everything.
So you guys have the cubes and also the phones and other devices to do experiments. I understand that they don't need to be connected to the internet to work. Is that correct?
They are basically talking, so getting feedback from the Windows teacher, but we can also cache them, and they can also work offline if this is the demand.
Yeah, that was my next question, because in most of the developing countries or rural areas, you might not have internet connection. So it can work with a local cache.
So earlier you guys gave us some projections about how many you think you'll be able to sell over the next few years. How many sets of cubes do you see one school owning, and how did you come up with those numbers?
So I was talking about how many cubes, how many kids will sell in each year, and how we came up with these numbers. So basically, we saw how many schools there are in our region, in our local region, then how many schools there are in our country, and we thought about 15 kids per school. And then we multiplied this, and we also presented our project to a company that already has educational projects, and they are making also equipment for schools. And we negotiated with them, we talked with them, and they told us, okay, in the first year, this is realistic. You can get your kids to this number of schools.
You know that Rubik's Cube, I don't know if it's the Romania or Czech. As you know that in the cube, the row is not only 2, they got 3 or 4. In the case, you can have many different combinations, and even in this case, I don't think you have many interesting results from the 2 cubes. You can have 3 or 4. Do that, resume that, demonstrate that. So in that case, probably the cube, the reason I asked the price of this, even though it is high end, probably the market, I don't think it is called for the poor people. It is more high end market, it will more make sense. You know what I mean?
Well, we actually thought about those kids with 6 cubes, so that with 6 cubes you can do a lot of things, such as words, and they can check if your grammar is correct, or any kind of game can be put on them.
Yeah, so that means the probably more better way to increase the potential of this cube, and also that lead to the different market rather than the
Yeah, that is our intention.
So basically, we are really talking with TechSoup. What TechSoup does, it gets money from companies, big companies like Microsoft and Cisco. Then it buys some reuse hardware like mobile phones, and for example, they have mobile phones in their product list for $30. So we are talking now with them to sell also our iQubes, yes, from that money, and give them to schools at a real cheaper cost. And also regarding to the many educational experiments and educational games that can be created, we talked with teachers and they came up with really good ideas and really vast ideas. They can make also music with them. On each cube a different note and then play the sounds. They can make literacy, they make words and also mathematics. So it's a lot of different areas in one product. Else they have to buy a lot of different educational material. So this is the add-on value.
One device.
But going into that, you compared that a fully equipped lab will go for around $3,000 a year, while your solution will go for around $1,000. Do you think it's fair to compare a fully equipped lab with your devices?
Of course not, but the fact is that many schools can't afford that $3,000. So what we offer them is an alternative, maybe not like a real laboratory equipment, but much more engaging than just computer simulations and at a lower cost. So if they can't buy the laboratory equipment, they have this lower price solution.
What's the difference between computer simulation and real simulation? I don't see any.
Our approach offers hands-on experience, and you actually see the results in your lab.
We don't have a realistic model. Just playing with cubes, and we are talking about biology, chemistry, and physics. There is no realistic model. When we are talking about school laboratory, you have realistic model. And if you are talking, it's not fair to this comparison. Yes, no. You can't compare it with laboratory with the realistic model.
Yes, you understand that, but we are thinking about the idea that it's better with the IQs than with nothing. That's what we
Okay, then compare to nothing and not.
And also for primary education, they don't have complex experiments. We just offer them something besides the textbooks. For children, they learn multiplication or summation by playing, and that's how education becomes more engaging for them. They will like education.
Okay, then focus on primary education. I'm not talking about secondary education and about physics and biology, because it has nothing with realistic model in physics and biology. It's chemistry especially.
And also comparing with the computers, when we went to the second grade, the teacher showed us that they installed the software and educational software on computers. And she really told us that the children have difficulties to use the computer. First, the mouse is not so intuitive, and first they search on the keyboard the letters in the alphabetic order, so they can't find them. And that way, we build the cubes especially for them, because it's a natural interface for them.
If you are talking about iPad generation, there is also all ability of interoperability between objects in your screen. I can do with my iPad all the things you can do with your iQubes, and it will be even more cheaper.
I've got one for you guys. Can you tell me about how long or how much training that you think that each of the teachers actually require to sit down and learn how to make the experiments effectively with students, if they want to make a brand new one?
I think if we put a tutorial that can begin to make them in a couple of hours, maybe one day. It's designed to be intuitive, and even the logic part is just something you would think about naturally. Well, what should happen if I connect to this cube in a certain way? And that's what it says. If this cube is connected to that cube, then do this. And you basically just select a block, do this or do that.
It doesn't depend on what kind of subject. For example, mathematics teacher, or chemistry teacher, biology teacher, they don't care?
They shouldn't care because that part is abstractized. In the first part, you decide what to put on each side of the cube in different scenarios, and then you say that you want it to display that. And that can be mathematics, that can be physics, that can be association games for kindergarten, animals, movies, whatever.
You guys showed us a couple of uses of the platform you built. Were there any applications or add-ons for it that you wanted to build that you didn't have time or you really like to see made in the future?
Yes, we want more cubes. We manufacture this by hand, so it's a long-run process to build them. And we also wanted to make them better with larger screens and a thinner bezel. But because we buy components in retail, we are limited to the choices because most want to sell them in 10,000 units.
Perhaps we could also make a back screen. And for the interface, the teacher interface, we can abstractize it even more to make it easier to make experiments.
Do you have any special reason you don't demonstrate here?
We have the stands.
I know, but we have to make a point here, and then that's it, and then we go to another one. I think it's better to demonstrate here.
No. Right, we don't have the
We can show them.
You have the...
We like to control it.
We'll say it later.
Yeah.
Right.
We'll see you a little bit later.
Hey, good job, guys. Congratulations, and see you later. Good job.
Thanks.
Congratulations.
Thank you.
Sorry?
That's mine or yours?